What if I told you that right now, at this very moment, you're traveling through space at 99.9999% the speed of light, and yet you're also completely stationary? What if the reason light can't go faster isn't because something is holding it back, but because light is literally defining what faster even means? And here's the part that will haunt you tonight. Every single particle in your body is desperately trying to move at light speed right now, but something invisible, something woven into the fabric of reality itself, is stopping you. In the next 3.5 hours, I'm going to show you something that will fundamentally change how you see reality. Because the speed of light isn't just a speed limit, it's a cosmic conspiracy that reveals we don't actually understand what speed, time, or even reality itself truly are. Imagine you're driving a car at 60 miles per hour, and you throw a baseball forward at 60 miles per hour. Common sense says the ball is now moving at 120 miles per hour relative to the ground, right? Now imagine you're on a spaceship, moving at 99% the speed of light, and you shine a flashlight forward. The light should be moving at 199% the speed of light, right? Wrong, dead wrong. And the reason why will unravel everything you thought you knew about the universe. Before we dive into this mind-bending journey, do me a favor, hit that like button and subscribe, because what you're about to learn isn't taught like this anywhere else. And drop a comment telling me what country you're watching from and what time it is there right now. I want to know how this message is spreading across spacetime itself. Let's start with what seems simple. What is light? You've been told light is made of photons, tiny particles of electromagnetic radiation. But here's your first cognitive earthquake. Light isn't really a thing that moves. Light is more like a cosmic speed limit enforcer, a universal constant that exists because of something far stranger. Think of it like this. Imagine you're in a video game. Your character can run at a certain maximum speed, right? No matter how many power-ups you collect, there's a hard-coded limit in the game's programming. Now, what if I told you that our universe is like that video game, but the programming is something called the structure of spacetime itself? In 1676, a Danish astronomer named Ole Reckmer made the first real measurement of light speed. He wasn't even trying to measure light. He was studying Jupiter's moon Io, and he noticed something bizarre. When Earth was moving away from Jupiter, Io seemed to orbit slower. When Earth moved toward Jupiter, Io seemed to orbit faster, but Io wasn't actually changing its orbit. Light from Io was taking different amounts of time to reach Earth, depending on the distance. Reckmer calculated that light traveled at about 220,000 kilometers per second. Not perfect, but remarkably close to the actual speed. 299,792,458 meters per second. But here's what's wild. Reckmer discovered light's speed, but he had no idea why it had a speed at all. For the next 2 centuries, scientists assumed light traveled through some invisible substance called the ether, like sound travels through air. If you moved through this ether, you should be able to measure yourself moving faster or slower relative to light, right? In 1887, 2 scientists named Albert Michelson and Edward Morley set up what should have been a simple experiment. They built an incredibly precise device called an interferometer that split light beams, sent them in perpendicular directions, and then recombined them. Here's the logic. Earth is orbiting the Sun at about 30 kilometers per second. As Earth plows through the ether, light going in the direction of Earth's motion should appear to move slightly slower, and light going perpendicular should move at a different speed, like trying to swim upstream versus across a river. They measured and measured and measured again. The result? Light always moved at the same speed, no matter which direction it was going, no matter how Earth was moving. It was as if they swam upstream in a river and found the water wasn't moving at all. Impossible. Nonsensical. Reality breaking. This is the moment physics broke. This is where everything we think we know about motion, time and space revealed itself to be a comfortable illusion. Because the only way light can always move at the same speed, regardless of how you're moving, is if something else is changing. And what's changing is something you consider absolute and unchangeable: time and space themselves. Here comes the revelation sandwich. I'm about to tell you something that sounds completely insane. Then we'll build the understanding, and then you'll realize it's not just true, it's the only way reality could possibly work. Ready? Time is not constant. Space is not constant. The only thing that's constant is the speed of light. And everything else, time, distance, simultaneity, even causality itself, bends and warps to keep light moving at exactly 299,792,458 meters per second in all reference frames. Let's build to this. In 1905, a 26-year-old patent clerk named Albert Einstein published a paper called On the Electrodynamics of Moving Bodies. No fancy lab, no university position, just pure thought. Einstein asked a simple question. What if the speed of light being constant wasn't a weird experimental result, but a fundamental law of nature? What if we've been thinking about this backwards? Think of it like this. Imagine you and I are standing on opposite sides of a river. I'm on the north bank. You're on the south bank. A leaf floats down the river between us. From my perspective, the leaf is moving south. From your perspective, the leaf is moving north. We disagree about the direction, but we're both right in our own reference frames. Motion is relative. Now, here's where it gets strange. Einstein said, what if the speed of light is like an absolute direction that everyone must agree on, regardless of their reference frame? The only way that's possible is if north and south themselves change depending on who's measuring. In other words, space and time have to be flexible to keep light's speed rigid. Let me give you a concrete example. Imagine you're on a spaceship traveling at 90% the speed of light, moving away from Earth. You shine a flashlight forward. From your perspective on the ship, the light leaves the flashlight at 299,792,458 meters per second, moving away from you. But here's the question. From Earth's perspective, how fast is that light moving? Your intuition says 90% light speed plus 100% light speed equals 190% light speed. But that can't be right, because the Michelson-Morley experiment proved light always moves at the same speed. So how fast is the light moving from Earth's perspective? Still 299,792,458 meters per second. The exact same speed. How is this possible? Because time on your spaceship is moving slower than time on Earth, and space on your spaceship is contracted compared to space on Earth. The mathematics of relativity aren't a theory about how the universe might work. They're a description of how the universe must work to keep light speed constant. Here's your second mind-blown moment. You're never at rest. Right now, you're sitting there, thinking you're stationary. But you're on Earth, which is spinning at about 1,670 kilometers per hour at the equator. Earth is orbiting the Sun at 107,000 kilometers per hour. The Sun is orbiting the galactic center at 720,000 kilometers per hour. Our galaxy is moving through space at 2.1 million kilometers per hour. And yet, if you turn on a flashlight, light leaves that flashlight at exactly 299,792,458 meters per second. Not faster because you're moving with the light. Not slower because you're moving against it. Exactly the same. Now we need to go deeper. Why does light move at this specific speed? Why not faster? Why not slower? And here's the question that will bend your brain. Does light actually move at all? What if I told you that from light's perspective, light could have a perspective? It doesn't move at all. From a photon's point of view, it is emitted and absorbed at the exact same instant. No time passes. The journey from the sun to your eye, which takes 8 minutes from your perspective, takes 0 time from the photon's perspective. Think of it like this. Imagine you're watching a movie. From your perspective, the characters are moving through time, experiencing events sequentially. But from the perspective of the film strip itself, all frames exist simultaneously. The beginning and end of the movie exist at the same time, just at different positions along the film. That's closer to light's experience of reality. But this raises a profound question. If light doesn't experience time, what does that mean for causality? What does that mean for cause and effect? Enter physicist James Clerk Maxwell. In the 1860s, Maxwell unified electricity and magnetism into a single theory of electromagnetism. His equations predicted that oscillating electric and magnetic fields could propagate through space as waves. When he calculated how fast these waves should move, he got a very specific number: 299,792,458 meters per second. The speed of light. This wasn't a coincidence. Maxwell had discovered that light is electromagnetism. But here's what's crucial. His equations showed that electromagnetic waves must propagate at this speed in a vacuum, not approximately, not on average, exactly. The speed wasn't a property of light, it was a property of empty space itself. Think of it like this. Imagine space is like a trampoline surface. When you drop a ball on a trampoline, it creates a depression, and waves ripple outward at a specific speed determined by the tension and elasticity of the trampoline material. The waves can't go faster or slower than the properties of the trampoline allow. Maxwell's equations revealed that space itself has properties specifically, something called permittivity and permeability, that determine how fast electromagnetic fields can propagate through it. But here's the part that should make your head spin. These properties of space, these cosmic constants that determine light's speed, they're not caused by anything. They just are. They're part of the fundamental structure of reality itself. You can't ask why the universe has these specific properties any more than you can ask why the number 3 exists. Physicist Richard Feynman, winner of the 1965 Nobel Prize in Physics, once said something profound. Why is nature the way it is? We don't know. We just take it as it comes. The speed of light is baked into the universe at the most fundamental level. It's not that something is stopping light from going faster, it's that faster than light is literally a meaningless concept in our universe, like asking what's north of the North Pole. Now here's where things get really weird. And I need you to pay close attention, because this is where most people's intuition completely fails them. We need to talk about mass. What if I told you that the reason you can't travel at light speed has nothing to do with engines or energy, and everything to do with the fact that you have mass? And what if I told you that mass itself is just stored energy, and that energy itself is just another form of... Well, let's build to that. Einstein's most famous equation, E equals mc. Energy equals mass times the speed of light squared. But what does this actually mean? It means mass and energy are the same thing, just in different forms. Mass is frozen energy. Energy is liberated mass. And the speed of light squared is the conversion factor between them. Think of it like this. Imagine money and gold are 2 forms of the same thing, wealth. The exchange rate tells you how to convert between them. Einstein discovered that mass and energy are 2 forms of the same thing, and the exchange rate is determined by light speed squared. But here's the crucial part. The reason light moves at light speed is because photons have 0 mass. They're pure energy. They have no choice but to move at the cosmic speed limit. But you're made of particles with mass. Electrons, protons, neutrons, they all have mass. And mass resists acceleration. Here's the equation that reveals the cosmic conspiracy. As an object with mass approaches light speed, its mass effectively increases. Not because it's gaining matter, but because energy has mass equivalence. And as you pump more energy into accelerating something, that energy itself contributes to the object's inertial mass. The faster you go, the more energy you need to go even faster. As you approach light speed, your effective mass approaches infinity, and the energy required to accelerate infinite mass to light speed is infinite. Let me make this concrete. Imagine you're in a rocket ship with unlimited fuel. You accelerate to 50% light speed. Cool, not too hard. Now you want to reach 90% light speed. You need significantly more energy, but okay, you make it. Now you want 99% light speed. Much, much harder, but possible. Now 99.9%. Now 99.99%. Now 99.9999%. Each additional decimal place requires exponentially more energy. To reach 100% actual light speed would require infinite energy, not just a lot of energy. Literally infinite. More energy than exists in the entire universe. This is why only massless particles, photons, gluons, gravitons, can travel at light speed. They don't have a choice. They must travel at light speed. They can't go slower, and they can't go faster. Light speed isn't a speed limit for them. It's their only speed. But here's your third mind-blown moment. Remember when I said that every particle in your body is trying to move at light speed? That's literally true. In the mathematics of relativity, every object is always moving through space-time at exactly light speed, not through space, through space-time. The four-dimensional combination of the three spatial dimensions and one time dimension. Stay with me here, because this is where your understanding of reality is about to completely invert. We need to talk about space-time as a single thing, not space and time as separate things. Imagine you're driving a car, and you can only move at exactly 60 miles per hour. No faster, no slower. But you can steer. You can go north, south, east, west, or any combination. Your total speed is always 60 miles per hour, but you can distribute that speed across different directions. In special relativity, you're always moving through space-time at light speed. Always. Right now, as you sit there motionless, you're moving through time at maximum speed. All of your motion through space-time is directed along the time dimension. But if you start moving through space, if you get up and walk, or drive a car, or board a spaceship, you're now diverting some of your motion from the time direction into the space directions. The faster you move through space, the slower you move through time. Not metaphorically, literally. This has been measured. This is experimental fact. Atomic clocks on fast-moving airplanes tick slower than stationary clocks on the ground. GPS satellites have to correct for time dilation, or your navigation would be off by miles. Think of it like this. Imagine a graph where the vertical axis is motion through time and the horizontal axis is motion through space. Your total motion, the arrow representing your movement through space-time, is always the same length, the speed of light. When you're stationary in space, your arrow points straight up pure motion through time. When you move through space, your arrow tilts. More spatial motion, less temporal motion. If you could move at light speed through space, your arrow would be perfectly horizontal all motion through space, zero motion through time. Time would stop. This is why light doesn't experience time. A photon emitted from a star, 1 billion light years away, reaches your eye in what is, from the photon's perspective, no time at all. The journey is instantaneous. The billion years is only from your perspective, from the perspective of someone moving slowly through space, and therefore rapidly through time. Physicist Brian Greene put it beautifully. The speed of light is the speed of time. Light doesn't move through time because it's already moving at maximum speed through space. All massless particles must do this. They have no choice. But here's the part that should make you dizzy. This means causality itself, cause and effect, is only possible because we move slowly through space. If we could move at light speed, causes and effects would be simultaneous from our perspective. The entire history of the universe, from Big Bang to heat death, would be compressed into a single eternal moment? This is the invisible rule stopping light from going faster. It's not going faster because it's already maxed out. It's moving at the universal speed limit through space-time. The question, why can't light go faster, is like asking, why can't a chess piece move in a way not allowed by the rules? The rules of space-time geometry dictate that the maximum speed through space alone is 299,792,458 meters per second. That's not a limit imposed on light, that's the structure of reality itself. Now let's talk about something that will seriously mess with your head. What if you could theoretically go faster than light? Not through normal space, but by bending space-time itself? What if I told you that the universe itself can expand faster than light, and in fact, it's doing that right now? Galaxies at the edge of the observable universe are receding from us faster than light speed, not because they're moving through space faster than light, but because the space between us and them is expanding faster than light can cross it. Think of it like this. Imagine two ants on a balloon surface. The ants can only crawl at a certain maximum speed across the rubber. But if someone blows up the balloon, the ants can move apart faster than their maximum crawling speed because the rubber itself is stretching. The ants aren't breaking their speed limit. The surface they're on is expanding. This is what's happening with cosmic expansion. Space itself is expanding. Distant galaxies aren't moving through space faster than light. Space is carrying them apart faster than light can cross the growing distance. This doesn't violate relativity because nothing is actually moving through space faster than light. In 1994, physicist Miguel Alcubierre proposed something wild, the Alcubierre drive. Imagine you could compress space in front of your spaceship and expand space behind it. You'd create a warp bubble where you're surfing on a wave of contracting and expanding space-time. Your ship wouldn't be moving through space faster than light. Space would be moving around your ship. You'd be stationary inside your bubble, while the bubble itself moves arbitrarily fast. Sounds like science fiction, right? Here's the thing. The mathematics work. The equations of general relativity allow this. The problem? You'd need exotic matter with negative energy density. And not just a little bit. You'd need more negative energy than there is positive energy in the observable universe. Oh, and creating it might destroy causality and create time travel paradoxes that tear reality apart. But mathematically, it's allowed. This reveals something profound. The speed limit isn't on objects moving through space. The speed limit is on information transfer, on causality. You can't send a signal or cause an effect faster than light. That's the real rule. If you could create paradoxes, send messages into your own past, violate causality, break the universe. Here's your fourth mind-blown moment. The speed of light is really the speed of causality. It's the speed at which effects can propagate from causes. It's the speed of information. It's the speed of reality updating itself. Think about it. When you flip a light switch, the signal doesn't travel down the wire instantaneously. It propagates at close to light speed. When the sun suddenly vanished, Earth would continue orbiting for 8 minutes before the gravitational effect reached us, because gravity propagates at light speed too. Every force, every interaction, every bit of information in the universe is limited by this cosmic speed limit. Let's dig into something that bridges classical physics and quantum mechanics, because the nature of light itself gets stranger the deeper we look. Light isn't just an electromagnetic wave moving at a fixed speed. It's also a particle, a photon, that exists in quantum superposition until observed. In 1900, Max Planck discovered that energy isn't continuous. It comes in discrete packets he called quanta. Light isn't a smooth wave. It's made of particle-like photons, each carrying a specific quantum of energy. This was the birth of quantum mechanics. But here's what's bizarre. When you're not looking, a photon isn't a particle traveling in a straight line. It's a probability wave that exists in multiple places simultaneously. The famous double-slit experiment proves this. Fire single photons at 2 slits, one at a time. Each photon somehow goes through both slits simultaneously and interferes with itself, creating an interference pattern. But the moment you measure which slit it goes through, the interference vanishes. The photon chooses one path. Think of it like this. Imagine you order food delivery. Until the food arrives, it exists in a quantum superposition of all possible routes the driver could take. But when you open the door, the delivery collapses into having taken one specific route. That's not really how it works, but it captures the weirdness. Observation changes reality at the quantum level. Now here's where this ties into light speed. The speed of light is also the speed of quantum information. When a quantum state collapses due to observation, that collapse can't propagate faster than light. This prevents quantum mechanics from creating paradoxes with relativity. Physicists Niels Bohr and Albert Einstein famously debated this. Einstein hated the implications of quantum mechanics. He proposed a thought experiment. If you create 2 entangled photons and send them in opposite directions, measuring one instantly affects the other, even if they're light years apart. Doesn't this violate the light speed limit? Here's the answer, discovered later. Quantum entanglement does create instant correlations, but you can't use it to send information faster than light. The correlations only reveal themselves when you compare measurements later, at light speed or slower. It's like 2 people opening matching envelopes simultaneously. The matching is instant, but it doesn't let them communicate. But this raises something profound. Why is the quantum world set up to respect the light speed limit? Why is reality so carefully constructed that even the weirdest quantum phenomena can't violate causality? The answer seems to be because the speed of light isn't really about light. It's about the structure of space-time itself. It's the maximum speed at which anything mass, energy, information, causality itself can propagate through reality. Physicist John Wheeler said, "Time is what keeps everything from happening at once. The speed of light is what enforces that separation. Without it, there would be no before and after, no causality, no ability for complex structures to form. The universe would be a single eternal frozen moment, or perhaps couldn't exist at all." Now we need to talk about something that sounds like pure science fiction, but is actually established physics: time travel. And before you roll your eyes, understand that time travel into the future is not only possible, it's been done. We've sent particles into their own futures. And the speed of light is the key that makes it work. Remember twin paradox? One twin stays on Earth. The other boards a spaceship that accelerates to near light speed, travels for what feels like 1 year to them, and returns. When they reunite, the traveling twin has aged 1 year, but the Earth twin has aged decades, centuries, millennia. It depends on how close to light speed the traveling twin got. This isn't hypothetical. We've measured this with atomic clocks. In 1971, physicists Joseph Haffel and Richard Keating flew atomic clocks on commercial airplanes around the world. When they compared them to clocks that stayed on the ground, the flying clocks had ticked slower by exactly the amount special relativity predicted, down to the nanosecond. Think of it like this. The closer you get to light speed, the more you're using up your motion through space-time on spatial movement, leaving less for temporal movement. You're moving through time in slow motion from everyone else's perspective. But from your perspective, time feels normal. It's the rest of the universe that seems to speed up. This means time travel to the future is trivially easy in principle. Just go really fast. The problem is engineering. To go fast enough for dramatic effects, you need absurd amounts of energy. To age 1 year while Earth ages a century, you'd need to travel at about 99.995% the speed of light for that entire year. The energy required would be more than humanity currently produces in decades. But here's something even stranger. General relativity, Einstein's theory of gravity, allows closed time-like curves paths through spacetime that loop back on themselves temporally. Near rotating black holes, near infinitely long rotating cylinders. In certain cosmic string configurations, you could theoretically travel into your own past. Physicist Kip Thorne, who won the 2017 Nobel Prize in Physics, showed that wormholes shortcuts through spacetime could theoretically be used for time travel. If you created a wormhole with one end moving at near light speed and one end stationary, the two ends would age at different rates. Eventually, the wormhole becomes a time machine. You enter one end and emerge from the other end in the past. The catch? Creating and stabilizing a wormhole requires exotic matter with negative energy density, the same stuff needed for warp drives. And even if you could create one, most physicists believe a chronology protection conjecture. Nature somehow prevents time machines from forming, perhaps through quantum effects that destroy them before they can operate. But here's your fifth mind-blown moment. The speed of light is what makes time travel paradoxes dangerous in the first place. If you could send information faster than light, you could send it into the past in certain reference frames. You could create a grandfather paradox without even trying. The light speed limit protects causality not by preventing time travel, but by making it so difficult and constrained that paradoxes can't easily form. Let's talk about black holes, because they represent the ultimate extreme of what happens when you push spacetime to its limits. And they reveal something shocking about the speed of light. Inside a black hole event horizon, the speed limit still exists, but it can't save you. A black hole forms when matter collapses to such extreme density that its gravity curves spacetime so severely that nothing, not even light, can escape from within a certain boundary called the event horizon. But here's what's truly bizarre. The event horizon isn't a physical surface. It's just a mathematical boundary in spacetime where the required escape velocity equals light speed. Think of it like this. On Earth, if you throw a ball up, it falls back down unless you throw it faster than escape velocity, about 11 kilometers per second. The Moon has lower escape velocity because it's less massive. The Sun has higher escape velocity. As an object gets denser, the escape velocity from its surface increases. When escape velocity reaches light speed, you have a black hole. But here's the mind-bending part. Once you cross the event horizon, every direction points toward the center. Not metaphorically, literally. The future direction in spacetime points toward the singularity. Escaping would require moving backward in time, which is impossible. The singularity isn't a place in space you're falling toward. It's a moment in time you're falling into. Physicist Stephen Hawking proved something remarkable about black holes in 1974. Black holes aren't completely black. They emit radiation due to quantum effects near the event horizon. Virtual particle pairs normally pop into and out of existence everywhere in space. But near an event horizon, one particle falls in while the other escapes. The escaping particle is called Hawking radiation. This is crucial. Hawking radiation is limited by the speed of light. It takes time for this radiation to escape and carry information away. A black hole evaporates, but slowly. A black hole with the mass of the Sun would take 1,067 years to evaporate, incomprehensibly longer than the current age of the universe. Here's what this reveals. Information might be preserved in black holes through Hawking radiation, but it's encoded in a way we don't fully understand. This is the black hole information paradox. Quantum mechanics says information can't be destroyed, but general relativity says black holes erase information. Solving this paradox requires a theory of quantum gravity we don't yet have. And the speed of light is central to this paradox. Information can only escape at light speed or slower. From an outside observer's perspective, anything falling into a black hole appears to freeze at the event horizon, its image redshifting and fading, but never quite crossing. This is because light from the falling object takes longer and longer to escape as it approaches the horizon, until effectively infinite time is required. But from the falling object's perspective, it crosses the horizon in finite time, then hits the singularity in finite time. The two perspectives are incompatible, yet both are correct within their own reference frames. The speed of light creates this cosmic disagreement about what's real. Now we need to address something mind-bending. Is the speed of light actually constant, or are we making an assumption? What if the speed of light has changed over cosmic history? What if it's different in different parts of the universe? This is called the variable speed of light hypothesis, and some physicists have seriously considered it. The idea is that in the very early universe, immediately after the Big Bang, the speed of light might have been different, perhaps much faster. This could solve certain cosmological puzzles, like the horizon problem. The horizon problem asks, why is the entire observable universe so uniform in temperature if regions on opposite sides of the sky were never in causal contact? If light has always traveled at its current speed, there hasn't been enough time since the Big Bang for light to travel from one side of the observable universe to the other. How did everything equilibrate to the same temperature? The standard answer is cosmic inflation, a period of exponential expansion in the first fraction of a second after the Big Bang. But an alternative is that light traveled faster back then, allowing different regions to interact and equilibrate before settling into the speed we measure today. Think of it like this. Imagine the universe is an orchestra, and the speed of light is the conductor's baton tempo. If the tempo was faster at the beginning, the musicians could synchronize before settling into the slower tempo we observe today. But here's the problem. Every test we've done shows the speed of light is constant. Fine structure constant, a dimensionless number that combines light speed, Planck's constant, and charge appears to be the same everywhere in the universe we can observe, going back billions of years. If light speed changed, this constant would change, and we'd see effects in atomic spectra from distant galaxies. We don't. Physicist Paul Davies proposed that while light speed might vary, other constants vary in lockstep, so all observable phenomena remain consistent. But this seems like adding epicycles to save a theory. Occam's razor suggests the simpler explanation. Light speed is truly constant. Yet here's something genuinely weird. Light doesn't always move at 299,792,458 meters per second through matter. When light passes through glass, water, or any transparent material, it slows down. In water, light moves at about 75% of its vacuum speed. In diamond, about 41%. But, and this is crucial, the light itself, the photons still move at light speed. What's happening is the photons are being absorbed and re-emitted by atoms in the material. The time delay between absorption and re-emission makes the average propagation speed slower. It's like driving through a city with lots of stoplights versus cruising on an empty highway. Your car's maximum speed doesn't change, but your average speed decreases. This is why we specify the speed of light in a vacuum. That's the cosmic speed limit. That's the invariant constant. 299,792,458 meters per second. Not faster, not slower, always the same for all observers in all reference frames. Let's talk about something practical. How does understanding light speed change technology? Because it's not just abstract physics, it affects your daily life in ways you probably don't realize. GPS satellites orbit Earth at about 20,000 kilometers altitude, moving at about 14,000 kilometers per hour. They carry atomic clocks that must be incredibly precise. Your position is calculated based on the time signals from multiple satellites. If those clocks are off by even a microsecond, your location could be wrong by hundreds of meters. But here's the thing. Those satellites are moving fast and are in a weaker gravitational field than Earth's surface. Special relativity says their clocks should run slower due to their motion. General relativity says their clocks should run faster due to weaker gravity. The two effects partially cancel, but don't fully balance. GPS engineers must account for these relativistic effects, or the system would fail within minutes. Think of it like this. The satellites are aging at a different rate than you are, not metaphorically, literally. Time is passing at a different rate for them. The speed of light and the curvature of spacetime must be accounted for in the GPS algorithm, or you'd never find your destination. The internet works at light speed, literally. Fiber optic cables carry data as light pulses. The theoretical maximum speed of information transfer is light speed. When you load a web page, you're limited by how fast light can travel through glass, about 200,000 kilometers per second in fiber. High-frequency trading firms exploit this. They place their servers as physically close to stock exchanges as possible because the time for information to travel at light speed can mean millions of dollars. A trading server in New Jersey has an advantage over one in California because light takes about 15 milliseconds to travel coast to coast. In high-frequency trading, that's an eternity. Particle accelerators like the Large Hadron Collider smash protons together at 99.9999991% the speed of light. At that speed, relativistic effects are huge. The protons' masses are increased by a factor of about 7,500 due to their kinetic energy. Time dilation means the protons experience the 27-kilometer LHC ring is only about 4 meters long due to length contraction. Think of it like this. We can accelerate particles to enormous energies, but we can never reach 100% light speed. We can get to 99.9999999999999%. Add as many nines as you want, but never quite 100%. The universe has an asymptote we approach, but can never touch. Now we need to talk about the biggest mystery in modern physics, dark energy. And it's deeply connected to the speed of light in ways that might surprise you. In 1998, 2 teams of astronomers studying distant supernova made a shocking discovery. They expected to find that the expansion of the universe was slowing down over time due to gravity. Instead, they found the expansion is accelerating. Galaxies are flying apart faster and faster. This discovery won the 2011 Nobel Prize in Physics. What could cause this? The leading explanation is dark energy, some mysterious property of empty space itself that creates a repulsive gravitational effect. About 68% of all energy in the universe is dark energy. We don't know what it is. We just observe its effects. But here's what's crucial. Dark energy has an energy density that appears constant everywhere in space. As the universe expands, more space is created, and more dark energy comes with it. The total amount of dark energy in the universe is increasing. Energy is being created from nothing. This seems to violate conservation of energy, but general relativity allows it energy conservation is local, not necessarily global in an expanding universe. Think of it like this. Imagine space is a fabric that's being stretched. As it stretches, the fabric doesn't get thinner. New fabric appears to maintain constant density. That's dark energy. And the rate at which space expands, the Hubble constant, determines how fast distant galaxies recede from us. Currently, the Hubble constant is about 70 kilometers per second per megaparsec. That means for every 3.26 million light-years of distance, the recession velocity increases by 70 kilometers per second. At about 4,200 megaparsecs, 13.7 billion light-years, galaxies are receding at light speed. Beyond that distance, they're receding faster than light. This is called the cosmological event horizon. Light from galaxies beyond this horizon will never reach us, no matter how long we wait, because the space between us is expanding faster than light can cross it. The observable universe, the region we can see, is limited by the speed of light, combined with cosmic expansion. Here's your 6th mind-blown moment. The universe is bigger than we can ever observe, and it's getting bigger faster than we can ever see. There are galaxies we can see, whose light will never reach us again, because expansion is carrying them beyond our light horizon. We're watching them disappear into a realm we can never access. The speed of light, combined with cosmic expansion, creates a cosmic blind spot that's growing. And in the far future, trillions of years, expansion will accelerate so much that even nearby galaxies will recede beyond our horizon. Future astronomers in the Milky Way would see an empty universe with all other galaxies having vanished. They would have no evidence of the Big Bang, no way to deduce cosmic history. The speed of light, which allows us to see the past, will also condemn future observers to ignorance. Let's dive into something that bridges multiple concepts: the cosmic microwave background and what it tells us about light speed and the early universe. The cosmic microwave background, CMB, is light from about 380,000 years after the Big Bang. Before this time, the universe was so hot and dense that it was opaque. Photons couldn't travel freely because they constantly scattered off electrons. But when the universe cooled enough for atoms to form, photons decoupled and began traveling freely through space. Those photons have been traveling ever since. Due to cosmic expansion, their wavelengths have been stretched, red-shifted, from visible light into microwaves. The CMB is the oldest light we can observe, a baby picture of the universe taken when it was just 380,000 years old. Think of it like this. Imagine a dense fog that clears suddenly. The moment the fog clears, you can see distant objects for the first time. The CMB is the light from that moment, the moment the cosmic fog cleared. And because light speed is finite, observing the CMB is like looking back in time to that moment. But here's something remarkable. The CMB is almost perfectly uniform in temperature, about 2.725 Kelvin everywhere in the sky. But almost is key. There are tiny fluctuations, about 1 part in 100,000. These fluctuations are the seeds of all structure in the universe: galaxies, clusters, everything. Physicists George Smoot and John Mather won the 2006 Nobel Prize for precisely measuring these fluctuations using the COBE satellite. Later missions like WMAP and Planck measured them even more precisely. The pattern of fluctuations reveals deep information about the universe, its age, composition, geometry, and the physics of the Big Bang. Here's what's profound. The speed of light determines the size of the largest fluctuations we see in the CMB. Since photons could only travel so far in 380,000 years, regions larger than that distance couldn't have influenced each other. The size of CMB fluctuations encodes the cosmic speed limit at work during the early universe. But there's a puzzle. The CMB is too uniform. Regions on opposite sides of the sky were never in causal contact. Light couldn't have traveled between them in the time available. How did they equilibrate to the same temperature? This is the horizon problem I mentioned earlier. The answer is cosmic inflation. In the first 10 to 32 seconds after the Big Bang, the universe expanded exponentially faster than light speed, not by objects moving through space, but by space itself expanding. In this brief instant, the universe grew by a factor of at least 1026, maybe much more. Think of it like this. Imagine two ants on opposite sides of a balloon. The balloon suddenly inflates to 1 trillion times its size in a microsecond. The ants never moved, the rubber expanded under them. That's inflation. It solved the horizon problem by inflating causally connected regions to cosmic scales. But inflation also reveals something important. The universe can expand faster than light because spacetime itself has no speed limit. Only objects moving through spacetime are limited to light speed. Spacetime itself can do whatever it wants. Now let's talk about the philosophical implications. What does the existence of a cosmic speed limit tell us about the nature of reality itself? Physicist Lee Smolin has argued that the speed of light, being finite and constant, suggests the universe is fundamentally computational. Information processing requires time. If light speed were infinite, information could propagate instantly, and the entire universe would update simultaneously. Causality would be meaningless. Think of it like this. Imagine reality is a vast computer simulation running on cosmic hardware. The processor has a clock speed, a maximum rate at which it can update the simulation. That clock speed is the speed of light. It's not that light is moving through a pre-existing space. Rather, light speed is the rate at which reality computes itself into existence. This is more than metaphor. It's called the holographic principle. In 1993, physicist Gerard 't Hooft proposed that all the information in a three-dimensional volume of space can be encoded on a two-dimensional surface surrounding that volume like a hologram. The speed of light determines the maximum information density and the rate of information transfer. Black hole physics supports this. Stephen Hawking and Jacob Bekenstein showed that a black hole's entropy, the amount of information it contains, is proportional to the surface area of its event horizon, not its volume. This is bizarre. Normally, entropy should scale with volume. More space equals more information. But for black holes, it scales with surface area. This suggests something profound. Reality might be holographic. What we experience as three-dimensional space might be information encoded on a distant two-dimensional surface. We're like characters in a 3D video game, unaware that we're really just 2D code being rendered by a graphics processor. Here's your seventh mind-blown moment. The speed of light might be the processing speed of the cosmic computer. The Planck length 1035 meters might be the pixel size of reality. The Planck time, y-43 seconds, might be the refresh rate. Below these scales, the concepts of space and time might not even exist, just quantum information being processed according to algorithms we call physical laws. This isn't science fiction. Physicist Edward Fredkin, physicist Stephen Wolfram, and others have seriously proposed that the universe is fundamentally a cellular automaton, a computational system where reality emerges from simple rules operating on a discrete grid. If true, the speed of light isn't a property of something called light moving through something called space. It's the fundamental clock speed of existence itself. The reason nothing can go faster is because faster has no meaning. You're asking the universe to compute faster than its processor can handle. Let's explore something cutting edge. What happens to our understanding of light speed when we try to unify quantum mechanics and general relativity into a theory of quantum gravity? String theory proposes that fundamental particles aren't point-like. They're one-dimensional vibrating strings. Different vibration modes correspond to different particles. A photon is one vibration mode. An electron is another. Gravitons, hypothetical particles of gravity, are yet another. In string theory, strings vibrate in a space with more than 3 spatial dimensions, possibly 10 or 11 total dimensions. The extra dimensions are curled up at scales too small to observe, around the Planck length. The speed of light emerges from the geometry of this higher dimensional space. Think of it like this. Imagine ants living on a garden hose. From far away, the hose looks one-dimensional. But to an ant, there's a second dimension around the circumference of the hose. If the hose is thin enough, the ant might not notice it's walking on a curved surface. That's like us living in a universe with hidden dimensions. But here's what's wild. In string theory, the speed of light isn't fundamental. It's derived from more basic quantities like the string tension and the geometry of the compactified dimensions. Change those parameters, and light speed changes. Loop quantum gravity, an alternative to string theory, proposes spacetime itself is quantized, made of discrete chunks. Space isn't continuous. It's a quantum foam of Planck-scale loops. Light doesn't travel smoothly through space. It hops from one quantum of space to the next. If this is true, light speed might actually vary slightly at extremely high energies. Ultra-high energy photons from distant gamma-ray bursts might travel slightly slower than low-energy photons due to quantum gravity effects. Observations haven't detected this yet, but future telescopes might. Physicist Carlo Rovelli, a founder of loop quantum gravity, suggests time itself might not be fundamental. Instead, time emerges from quantum correlations between different parts of the universe. If he's right, the speed of light isn't the speed at which something moves through time. It's the rate at which quantum correlations propagate between different regions of the quantum foam. Think of it like this. Imagine reality is a vast network of connected nodes, like a social network. Time isn't the background in which the network exists. Time is the process of information spreading across the network. The speed of light is the maximum rate at which one node can influence another. Now let's bring this back to you. How does all this affect your life? How should knowing that reality has a cosmic speed limit change your perspective? First, understand that you are a creature of time. You exist only because causality exists. Cause and effect, action and consequence, memory and anticipation all depend on the speed of light being finite and constant. If light speed were infinite, your thoughts couldn't form. Neurons fire by transmitting electrical and chemical signals that propagate at speeds limited by light speed. Your consciousness exists only because the universe has a speed limit. Think of it like this. Your brain is a temporal machine. It creates the experience of now by integrating information from the recent past and predicting the near future. But this only works because information takes time to propagate. The speed of light, combined with the speed of neural signals, creates the subjective experience of time flow. When you look at the stars, you're literally seeing the past. The light from the sun is 8 minutes old. Light from the nearest star, Proxima Centauri, is 4.2 years old. Light from the Andromeda Galaxy is 2.5 million years old. You're not seeing these objects as they are now. You're seeing them as they were when the light left them. This means the concept of now across the universe is meaningless. There is no universal present moment. Your now is different from someone else's now if you're in different reference frames. The speed of light creates a cosmic web of delayed information where every observer experiences a slightly different version of the present moment. Here's something beautiful. You are made of atoms forged in stars that exploded billions of years ago. Those atoms traveled through space for eons before gathering into the planet you live on. Every atom in your body is a time traveler, and the speed of light is what allowed them to reach you. But you're also literally made of light. E equals mc means the mass of your body is equivalent to an enormous amount of energy, about 1,018 joules for an average person, equivalent to about 21 megatons of TNT. That energy is locked inside you, held together by forces that propagate at light speed. You are frozen light, shaped into consciousness. Physicist Richard Feynman said, "Atoms are made of electrons and nuclei. The nuclei are made of protons and neutrons. Those are made of quarks held together by gluons." What are quarks and gluons made of? Excitations in quantum fields. What are quantum fields? We don't know, but they obey rules that include the speed of light as a fundamental constant. You are excitations in quantum fields, dancing to rhythms set by the cosmic speed limit. You are temporary patterns in the quantum foam, existing only because the universe has a speed limit that allows structure, causality, and consciousness to emerge. Now let's talk about the big picture. What does the speed of light tell us about our place in the cosmos? The observable universe is a sphere about 93 billion light years in diameter, centered on Earth. But that's just what we can see, the region from which light has had time to reach us since the Big Bang. The actual universe is likely much, much larger, possibly infinite. But due to the finite speed of light and cosmic expansion, we are causally disconnected from most of the universe. There are regions we can never observe, never reach, never influence. The speed of light doesn't just limit how fast we can travel, it defines the boundaries of the knowable universe. Think of it like this. Imagine you're on an island in an infinite ocean. You can only see to the horizon. You know there's more ocean beyond, but you can't see it or reach it. That's us. The cosmic horizon defined by light speed is our island's edge. But here's something humbling. Future intelligent beings in the far universe, trillions of years from now, will live in an even more isolated cosmos. As dark energy accelerates expansion, their observable universe will shrink. Eventually, they might only see their local galaxy, with all others having receded beyond the cosmic horizon. They would have no way to learn about the Big Bang, cosmic expansion, or the deep history of the universe. We are fortunate to live in a cosmological era where we can observe the CMB, measure cosmic expansion, and piece together the universe's history. This window of opportunity won't last forever. The speed of light, combined with cosmic expansion, means future civilizations will be cosmologically impoverished compared to us. Physicist Lawrence Krauss wrote about this in A Universe from Nothing. He points out that every observation of the distant universe is an observation of the past. The universe we see is not the universe as it is now. It's a patchwork of different moments in cosmic history, all stitched together by the finite speed of light. Here's your 8th mind-blown moment. You have never seen anything as it truly is in the present moment. You see your own hand as it was nanoseconds ago, the time for light to travel from hand to eye. You see the moon as it was 1.3 seconds ago. You see the sun as it was 8 minutes ago. Everything you experience is the past. Your entire lived experience is a collage of different moments in time, unified by your brain into the illusion of a single present. The speed of light doesn't just limit how fast information travels. It creates the very structure of your experiential reality. And here's something profound. The universe might be teeming with life, but we'll never meet most of it. If intelligent life exists on a planet 1,000 light years away, any message we send would take 1,000 years to arrive, and their response would take another 1,000 years to return. A single exchange of messages takes longer than human civilization has existed. The speed of light makes the universe incomprehensibly vast and incomprehensibly lonely. We are islands of consciousness separated by gulfs of space and time that we can never truly bridge. So, what invisible rule stops light from going faster? The answer, after this long journey, is this: nothing stops light from going faster. Light is already maxed out. It's moving at the only speed it can move, the speed of causality, the speed of information, the speed at which reality itself updates. The speed of light isn't a property of light. It's a property of spacetime. It's the cosmic speed limit baked into the geometry of existence itself. Massless particles like photons must travel at this speed because they have no choice. Particles with mass can never reach this speed because doing so would require infinite energy. The universe has an asymptotal limit we approach, but can never touch. But deeper than that, the speed of light is the rate at which one moment of time transforms into the next. It's the cosmic clock speed, the fundamental frequency of reality. Without it, there would be no causality, no time, no structure, no us. You are a temporary arrangement of atoms held together by forces propagating at light speed, experiencing a flow of time created by the finite speed of information, observing a universe whose boundaries are defined by how far light can travel in cosmic history. You are a child of light, living in a universe where light defines the very fabric of existence. The invisible rule stopping light from going faster is the same rule that allows you to exist in the first place. It's not a limitation, it's the structure of reality itself, and it's beautiful. Thank you for joining me on this journey through space-time. If this changed how you see reality, hit that like button, subscribe for more mind-bending explorations of physics, and drop a comment sharing which concept blew your mind the most. Remember, you're not just made of atoms, you're made of stories. And this is one of the greatest stories the universe has to tell. Until next time, keep questioning, keep learning, and keep looking up at the stars. They're not just distant lights, they're time machines, showing you the universe as it was. And you are the universe experiencing itself, one Planck time at a time.